Hello students. So any doubts? I have posted the quiz 2 solutions. Okay, so last live sessions we had some questions on quiz 2. So I have prepared the solutions and posted. Okay, so video lecture number 41 is devoted to quiz 2 solutions only. Okay. So any questions from any chapters? So not only chapter 8. I will prefer chapter 8 first, and after that we can answer any question from any chapters. Chapter 8, second question. Okay. Yes, so there is a system given here. This is a design problem, remember that. Okay, so answer may vary depending on the question. Sometimes it gives you the range. So here it is. So this is RS, and then.
So do we have to assume ourselves in the question? Values?
Say again.
So do we have to assume the values?
Assume the values. Yes. And finally you have to decide. So when you have like a maximum overshoot of 20% or less, that means you have quite a few range basically. So that way you have to. And when you say settling time 2 seconds, so that means what it fixes is zeta times omega n. But overshoot is 20%. That really means that or less. That really means zeta may have different values. So accordingly, omega n may also change. So you have quite a range of values. Got it? So it is not one solution. It could be many solutions.
So because in first question also, I was not able to get the values of all the all the components separately. It was coming together, combined only. So we'll have to assume.
Yes, you have to assume then. Yeah. So design problems are like that only. So finally you have to come up with some values.
Yeah? So do we have any basis for assuming that what value we should assume?
No, as long as all the equations are satisfied, you are fine.
Okay, sir.
Yeah. So the design problems have, design. That's why you have a lot of designs, right? It's not a single solution. Yeah. So solution could be different. So you have to just come up with one solution. That's it. Yeah. Yeah. Otherwise, it is fine, or still you want the solution of this?
Yes, sir. Please do the second question.
Okay. Okay. So here it is. To s plus 2 divided by s plus 1 divided by s plus 10. And here CS and okay. So what it says, determine the k. So value k equal to what, a equal to what, and b equal to what. So this is design problem basically, and you have to find out this parameter that the response to the unit step disturbance input and the response to the unit step reference input satisfy the following specifications. The response to the step disturbance input should attenuate rapidly with no steady state error. and the response to step reference input exhibits a maximum overshoot of 20% or less in a settling time of 2 seconds. Yeah, so here there are two things it is asking. In the what you have to find out is first CS over DS, and for that, if DS is what it asks you, say if DS is equal to step input, that's 1 over S, then CT as limited t tends to infinity should 0. So it should die out, right? So this is attenuate rapidly. So fine, and no steady state error. So when it means, actually there's some language here, you have to be careful here. The idea of a good control system is not to be disturbed by any disturbance. That means if there is a step input, it should not be reflected in the output. That's what the meaning is. Meaning that if ds equal to 1 over s, that is step input, then it should not have any long-term effect. Meaning that at t, when t tends to infinity, the value should be 0. That's what it means. That's a steady state. Means it should attenuate, and there should no steady state error. Meaning that it's a die out, and the value should be 0. That's what it means. Okay. So that means you have to find out this first, and we have to see whether it is doing that or not. Okay. So that's one thing. Second thing is says if you have to find out this, and also CS over RS. In the second case is if RS equal to 1 over S, then it is telling you the maximum overshoot MP should be less than equal to 20%, and settling time TS should be equal to 2 seconds. Okay. So how to solve it? Okay, so let's check this one in the what is the value of CS over DS first, and then accordingly we can do it, right? So CS over RS you can find out first CS over DS. So if you look at here, when you are calculating CS over DS, assume you are going to just see the effect because of the disturbance only. So you will assume RS equal to 0. And from here you are going to calculate. So what you find out right now, this will be simply will be ds here, right? And then it will be 2s plus 2 divided by s plus 1 multiplied by s plus 10, right? And it will be cs here, and this you can you see here it coming from minus cs, right? And then it goes here, so minus cs times that it is going to here. So it is a kind, it actually becomes a kind of the negative feedback loop only. Yeah, so it becomes, you can write like k as plus 1 bs plus 1 divided by s. Yeah, and then like this. Yeah, and this minus, and this becomes plus here. Yeah, so this is how it will look like. Yeah, so simplified, when RS you make equal to 0, it will be simply like this one. Okay, if that is so, then you can find out the CS over DS. CS over DS, you can find out will be equal to, so that this will be G, this will be H, and you can find.
Sir, I can tell you the final equation, like
yeah,
CS upon DS finally.
Yeah,
sir,
okay.
It's coming
Okay,
2s s plus 2
yeah
divided by s cube bracket 1 plus 2 times KAB, and then separately.
Okay, so there will be some here, some value here, right? In K.
Yes, sir.
K will be in SQ or something like that, right?
Yes, sir. Yes, sir.
Yeah. So there will be some SQ and some value. And,
S square term.
Yeah, there will be some constant at the finally, right? Some constant plus some constant, right?
4K. Yes, sir.
Yeah. Okay. So that's what you get, right? 2 times s plus 2 multiplied by s, right? That's what you get. So you can see that if we have if ds equal to 1 over s, right? So cs will be equal to 1 divided by s multiplied by this, right? So we can say that cs equal to 1 over s times this, right? That means the steady state c, that is limit t tends to infinity, c t will be equal to s limit, sorry, t equal to infinity, limit s tend to 0 scs, right? So this s and this s will come cancel out, and what we will get in limit s tend to 0, and this you will have this value 2 s plus 2 times s divided by all those things, right? S cube and whatever you have. So what you get is, if you get equal to 0, yeah, you are getting 0 because s term is there, right, in numerator. So a steady state will be 0. That means for the step input of disturbance, finally the value is going to be 0. That's what it tells you. Yeah, it's okay.
Yes, sir.
So that means we have already this satisfies this satisfying, and then we have to worry about something else. Then we have to see the next one, right? So the first one is automatically taken care of. Yeah, so there's no problem. Yeah. So okay. So now next is we have to find out this one. Okay. So this for that we have to find out the new transfer function. Okay, so now we can assume ds equal to 0, and then we can find out cs over rs will be equal to this now multiplied by this directly and divided by like this, right? So what we get in that case will be simply whatever the value of here divided by, yeah, and then we get 1 plus, and then we have this k as plus 1 bs plus 1 divided by s multiplied by 2s plus 2 divided by s plus 1 s plus 10, right? Right, and same thing will be here also. Yeah, so exactly the same thing will be here as well. Okay, now what do you want to find out? So here we are not looking at right now what the value is, because we know that we can just work on this open loop transfer function, and based on that we can design, right? So it's not important to know what it is, but we know that this will be simply this here only, right? Okay, now a few things are given, right? So settling time is given. Okay, when you say settling time, that really means few things are given. Uh, uh, like zeta is given to be specific, and you know you know that the settling time is nothing. Ts equal to 4 times t, where t is the or tau. The tau is a time constant equal to 4, where time constant is zeta time omega n. Yeah. So we are taking 2% rule. Okay, so we have this value, and that is equal to 2 seconds. Yeah, and that really means zeta omega n equal to 4 divided by 2 equal to 2, right? 2 per second. Yeah. So from here, what we know is zeta omega n value, right? So zeta omega n is known. Okay. Now what is given is this maximum overshoot. So maximum overshoot, we know that this is equal to E minus pi zeta divided by 1 minus zeta square, right? Is what it is?
The root
Right?
over.
It should be root, yes. Okay. So from this one multiplied by 100, right? And that is should be 20%, yeah. and hence we can find out the value. So from here we find out zeta equal to 1, right? So we get, so zeta is known. Okay, and now if zeta is known, okay, it says this or less. Remember, right? So or less. That's what it tells. Okay, so that means you will get the zeta should be greater than some value. So it will tell you simply zeta has to be greater than zeta naught, where zeta naught corresponds to 20%. So this is, you will get this value. Okay, now you can design by any method. Yeah, so you can look at a root locus, for example. Yeah, so root locus, from there, root locus exactly tells you when you vary k, then how the things are changing. Yeah, so root locus is the best way to actually design it. Yeah, so chapter 8 is about like only designing the PID by using any method, whatever you have learned, finally you have to apply. So it's a design only, right? So you can draw the root locus for this one. Yeah, root locus, you know that works for. I mean, only what you need is the open loop transfer function. Yeah, and then you can draw it. So how will you do it? So let's say you have like this. Okay. Now what are we doing? So let's look at the poles first. So we have the poles. So just a minute. So we have the poles. So let's say the pole, first pole is here. Yeah. Then s minus 1. So there is here is a minus 1. And then we have minus 10. So let's say minus 10 is here. Right? So this is minus 10. Okay. So we get all those things. Yeah. And then these things we don't know. Another is s plus 2, so minus 2. So there is a 0 as minus 2. So we have like this one. Yeah, now we have to design this. Yeah, so what is fixed here is zeta has to be greater than this one. And how do you, like, what is the meaning of zeta on this when in S plane? Zeta really means that it has to be so like this. This tells you some value here, yeah. And if this is phi, let us
omega
say,
n.
Yeah.
So that will give us omega n. So
Yeah.
we'll actually have the value of zeta and omega n by this range.
Yeah, but you know zeta also, right? You have zeta value, zeta greater than zeta naught, right?
Yes.
And yeah, and this this length from 0 here to a point will give you omega n, and this value from here to here gives you omega d. Basically, this is here, it is omega d, and here from here to here, distance from here to here is zeta omega n. So from here to here, zeta omega n, from here to here, omega d, which is equal to omega n multiplied by 1 minus zeta square, right? And that really means that cos phi, actually cos phi, this is cos phi will be equal to this, which is zeta omega n divided by omega equal to zeta, right? So cos phi gives you zeta. So that really means the smaller phi will give you higher zeta, right? For example, cos 0 will make it zeta equal to 1. Hence, what you want is, you don't want this side, you want everything on that side, right? This side. Yeah. Got it? And this will be mirror image, so accordingly, here also it should be like this. Yeah. So your point, your root cannot be this side of this. Yeah. So it has to be this side. That's what it tells you. So zeta. So this corresponds to, this phi will correspond to phi naught equal to zeta naught. Yeah. So you will find out the phi naught, and that is going to fix, right? Now your the values of these means the final operating point has to be on this side only. That's what it is telling you. Actually the roots of the characteristic equation has to be confined to left side of these lines, right? Okay, so far?
Yes, sir.
Okay. Now next thing is what you are given is zeta. Here it says zeta omega n equal to 2, and you know that zeta omega n is equal to, here when it is called 2, that really means it has to be here somewhere, right? So it is telling you that the roots of the characteristic equation has to be on this line, right? That's what it is going to tell, right? So because this is zeta omega n, and this zeta omega n is 2, and this is the value. So this line, vertical line, passing through -2, on that line, the roots of the characteristic equation has to be there. So it can be here or here or here or here or here, or even on the line, but not beyond that. That's what it's telling you. Yeah. So this is fixing it because zeta omega n is fixed. Hence, zeta omega n is fixed to this value right here, which will be equal to 2. Yeah, got it?
Yes, sir.
Yeah. Yeah. Now you have to choose which point you want. So now it's up to you. So any point you can choose here. So let us say you are choosing this point. Yeah. Close to that, you are using that point. Okay. Now what it says that it has to die out quickly. So that really means this is telling you that the first one telling you that dying out quickly will be when you have zeta, which is actually basically larger. Yeah. So when you have so little bit, if you very small, for example, sorry, if zeta is very large, no, so if zeta is here, let us say here, I mean zeta equal to 1, then it takes a long time to attain the final value. But if zeta is smaller, then it immediately goes up and tries to reach the steady state very soon. So but in this case already the zeta is there, so you don't want to be as close to this real axis, so it should be close to the upper bound. Yeah. Or you can just choose this point as well. Yeah. So let us say, regardless of that, let us say you have chosen this point, then you have to find out where. So you want the root locus, this point you have chosen, and you want the root locus to pass through this point now. That's what you want, right? Okay. So how will you decide? Okay, for that we are going to have you apply the angle rule. Yeah. So you are going to connect this point, connect this point, connect this point, and this point. Yeah. So for this chosen point, what you have is angles you already have, right? So this one is pole. So let us say this is theta 1, this is theta 2, and this is theta 3. So you can exactly measure what these values are, and this is 90 degree. Yeah. So let's call it phi 1 for zeros. Okay. So if that is the point here, so the value should match. Match means should be how much? So it should be theta 1, the zeros will come first. So 0 is here. So phi 1, we have phi 1 minus theta 1 minus theta 2 minus theta 3. Yeah. And there are two unknowns, 0. Here is the design part. Yeah. So there are two unknown zeros. So you want to place such a way. So let us say because of the first one is a phi 2, and this is a phi 3. So because of this is a phi 1, this makes phi 1, this root, sorry, this 0, sorry, phi 2, sorry, this is phi 3. So since these are zeros, so phi 1 plus phi 2 plus phi 3 minus theta 1 minus theta 2 minus theta 3 has to be plus minus 180 degree. Yeah, and then you can also have 2k plus 1, where you can have k varies from 0 to n, right? So as long as it satisfies this one, that will be on the root locus. Yeah, okay. So now phi 1 is known, theta 1 is known, theta 2 is known, theta 3 is known, and hence phi 1, phi 2 you can exactly get phi 2 plus phi 3 equal to plus minus 180 degree, 2k plus 1, then you get plus theta 1 plus theta 2 plus theta 3, yeah, and minus phi 1. You get exactly the sum of two angles that will satisfy the equation. Yeah. Once you have that, you know that theta 2 plus the phi 2 plus phi 3 has to be this value, and then once you know that, you will exactly know where to place it. Only thing is you have lot of choices. Yeah. So either you can have here or here or wherever. Yeah. So 2 points you have to choose such a way phi 2 plus phi 3 equal to this angle satisfied, and once you know the angle, you will know the points. Let's say you have decided this point and the other is this point. Yeah, this one. So such that this is, let's say, called phi 2 and this is a phi 3. Once you know phi 2, you draw a line from here at angle phi 2, wherever it meets, that will be s equal to, will be minus 1 over a, right? That's what that point will be, and this will be s equal to minus 1 over b, right? And hence you can find out the value of a and b from there. Okay, so once you have all those values, you can draw a root locus. You can find out exactly the value of k. So there will be some root locus maybe going like this. Yeah, something like it will go, and you can find out the value of k for this point. So you will get k as well. Yeah, it makes sense.
Yes, sir.
Okay. So this is a design problem. So design goes like this one only. Okay. So design has a lot of solutions. Because of this lockdown, we could not have the exams, paper and pen exam. Otherwise, we could have given the design problems. Yeah, but we will see if it is possible. We will do something about it. The questions, it may be there. Yeah. So any other doubt?
No, sir.
Okay.
Many questions. Diagrams. We observe that somewhere in the examples of the book they have done like shifting like h and then making it h by g. But how do we do that? Because it simplifies the
Shifting
problem.
edge. No, I did not get you. So if there's a G, so something like G and like this one.
So like a
We have
complex
H.
diagram is given. Like complex diagram is given, many G's and many H and
Okay.
many feedback loops.
Okay.
So this was in the
Yeah.
initial chapters also and in this chapter also.
Right.
Sir,
Okay.
in the example in the book, they have done like very easily that shift from this here from here and make it h by g, and I'm not able to understand how are they shifting from here to here.
Okay, so I have not seen that. Okay, I have not seen. So if you send me the some example problem, okay, then I will look at. Yeah. Yeah. But again, this
Sir,
is all.
otherwise by basics it's easy. Like by basics I'm able to do it, but it takes time. But yeah, it takes time only that.
Yeah. Okay. Uh, yeah. I mean, see, I think finally it all comes from the basics only. So that may be something, but I have not noticed that. Okay. So yeah. So if you send me the example, which one you are talking about, then we will have one last live session before the exam sometime. Okay, so that time I can talk about. Yeah, only thing I have not noticed. Yeah, so because of that.
Okay.
But in any case, if you have this kind of thing, uh, you can also think in terms of like combining them one at a time. You can combine. Yeah, so for example, if it is like given like one plus here and then you have another plus here, so automatically you write them together rather than writing separately. You can write them together. So and also you know that if it is if it is goes like this one, then you know that the whole thing, this one, you can write it as it is a minus here, and it is going like this. If it's G and this is H here, and you know that between this point to this point, you can simplify it as simply this will be equal to G over 1 plus GH. You can do that, right? So the whole loop will be equal to this one. So this kind of, but this comes from your experience. Right? It comes from your experience that if there is a negative feedback loop, then we will have this value. So the whole block is being replaced by this block. Yeah. So this kind of thing you can do, but what we are talking about actually, no idea. Yeah. So please send me the which example you are talking about.
Okay, sir.
Yeah. Also, like root locus as such is quite powerful, and you can think everything in terms of root locus, whether it's a Nyquist criterion we're talking about, whether finding out the angles. When you have confusion, why minus 180 degree and all those things, right? Minus 90 or plus 80, all those things. It has a meaning, I think. Yeah. So what is the meaning? Just I'm going to just a little bit tell about it. I think I should have covered this more, just to the insight part. Okay. So, but it's okay. So I'm giving you some insight, basically how you look at all those Nyquist diagram or Nyquist criteria from the root locus point of view, or whether root locus will help you to understand those. So let us say we have uh, like open loop transfer function gs equal to, let us say we have 1 over uh, s plus 1 times s plus 2. We have something like this one. Yeah. So now if you have to find out like how to plot Nyquist diagram, for example, for this one, just looking at that. Okay, so just we want to find out the way something like can we get something uh, from the root locus. Okay, so in root locus typically you have k here and you are moving the k. Yeah, so it doesn't matter. So this is for just for understanding. This is open loop transfer function, right? So this is open loop. Okay. Now the root locus as such, here will be simply this will be -1 and here -2. You know that it will be like this one, and from here the root locus simply. I mean, what is the when we are talking about the Nyquist diagram, we are talking about only this imaginary line, right? So it is talking about, like all others, we are not talking about the circular arc where it will be anyway it is going to be 0. Yeah, so we are not talking about that. But this boundary is very important when it moves from minus I infinity to plus I infinity. Yeah, so omega is going from minus infinity to plus infinity. So on omega we are talking about. Okay, so now let us say we have to draw the Bode diagram, right? So we have to draw like whether it's minus 80 or 80. What is the meaning of that? We can also look at from the root locus point of view. That what you understand here is, let us say there is a point here, because your values are going. When you are moving on this line, then what happens? When you are moving on this line, that's what the Nyquist plot is. So you will see that there will be two angles here, right? So there are two angles. Yeah. So here it will be, let us call it θ1. This is θ2. Yeah. Okay. So the angle, the total angle here will be equal to, angle will be simply, you see here, the angle of GS will give you an angle of this is 0, right? 0 minus angle of S plus 1 minus angle of S plus 2. You can relate to this one. What is the meaning? It tells you at 0 minus angle of S plus 1 is this one. Minus θ1 it gives you, and minus θ2 it gives you. Basically, you can relate from here. Yeah? And then you see that when omega tends to infinity, if this point is far, far away above, then what happens? If omega tends to infinity, then θ2 tends to 90 degree, and θ1 also tends to 90 degree. And hence, this value, the gi omega, right? Angle of this gi omega as omega tends to infinity becomes basically what? 0 minus 190 degree minus 90 degree, right? Equal to minus 180 degree. So you can relate from there also. Yeah. So always try to verify from different methods. So this controls is actually concept is very simple. Only one concept, and that is that the real part of the root should not go on the right side of the S-plane. That's it. And based on that, everything is there to easily plot it, just to see how stable it is and all those things. But here you can visualize it based on that. Yeah. Okay. So you can now, you know now that what will be the range of this from where to where it will vary. So if omega tends to 0, then what happens? Then θ1 is 0, θ2 is 0, and hence you have angle of g I omega equal to 0 only. What you see here simply, it varies from 0 to minus 180 degree. That's what you see when omega is going to from 0 to infinity. Hence, you can immediately draw the phase diagram for the Bode plot, right? So, and that will be what? It will be simply to be 0, and it will go to minus 0 here, minus 180 degrees. So you are seeing that how it is going. Yeah. Okay. Similarly, you can also see the magnitude diagram, right? So if you want to see what is the value of gi omega, right? So how to find out? So graphically, what is the meaning of that? So you can see here. So let's the point is called, this is pole 1, so P1, this is P2, yeah, and let's then call it, this one is as a point P. Yeah? Okay, so this is a P1, P2 point. Let's call point A. So okay, so this is a just let's call it point A here, point B, that will simplify. It will not be confusing. I will call point C. Okay. Now, what we see here is what we want is magnitude. Right? So magnitude. What is the magnitude? So G I omega. That's what we plot. Right. So in Bode diagram also we plot it. In Nyquist diagram also we plot it. Yeah. So how to relate it with the root locus plot or the S plane basically. Yeah? So here, what we actually is not, we are talking about a root locus plot, but this is the idea how you plot the root locus. So the angle has to satisfy the magnitude has to be satisfied. So on that basis, actually, yeah. So root locus when k you vary, that is talking about. But right now we're talking about is actually not necessarily the all angles are adding up to 180 degree. Yeah. So could be any angle. So, but we are using the same concept, whatever you learned during the root locus. Yeah? So this magnitude G I omega will be equal to magnitude of k divided by magnitude of S plus 1 and then magnitude of S plus 2. And that really means what? That really means that it will be k divided by S plus 1. So from here to here, so this will be AC, right? What is the length of AC divided by length of BC? That's it. Yeah, so this is how it will be. Graphically, you can actually find out the values, yeah, and accordingly you are going to plot it. Yeah, so in when you are plotting Nyquist plot, then you make k equal to 1, you can assume. Yeah, so and for that you are plotting, and then you will know when if you increase the k, you are going to zoom in basically. Yeah, so like that. So this also tells you that from here to here how they are related, and then you can, based on this one, you know that if you omega is 0, you are here, then you can find out exactly what the value will be. So let's say k equal to 1, yeah, and then omega equal to 0. When omega equal to 0, this point C will be here, and hence you can find out the value of G0, yeah, and that will be equal to 1 over 1 multiplied by this 1 here to here is 2, right, equal to half. You get value from right from there. You know that when omega equal to 0, the value has to be half. Okay, you also know from here, if omega tends to infinity, then what will be the value? Yeah, so omega tends to infinity, both of them becomes infinity, so value will be 0, right? So hence G I infinity will be equal to 0. Yeah, so you are getting the what is the meaning of that, right? Yeah. So this is one insight basically. So I think this course has a lot of insight, and especially you are looking at the same thing from different perspective. That also makes it very insightful. Yeah, so should not go just by equations. Just also see what is the meaning, why it is saying like this and that. Okay. Any other question?
No, sir.
Okay. Okay, then all the best for your quiz. Okay, it is scheduled tomorrow.
So the timing would be 11 a.m. only?
Yeah, 11 to 12, yes.
Yes.
Okay. Okay, see you later.